All right. Thanks for inviting me. And today I'll be very excited to present several joint work with my wonderful collaborators on using hardware-aware sparsity to perform accurate and efficient foundation model training. So in recent years, foundation models has made great contributions in image synthesis, language modeling, or scientific discovery. For example, you probably all heard this, models like AlphaFold, GPT-3, ChatGPT, Imagen, and so on. However, while achieving those great performance, they're very expensive to train, of course. This is mainly because the model and data size are exponentially growing, and the computation is usually performed on costly data center hardware. For example, a single training run of GPT-3 will take 4 months on 1,000 GPUs and cost $10 million, and at the same time produce massive carbon footprint. Therefore, with this limited resource in practice, we definitely have to overcome these bottlenecks and find more efficient ways to perform this large-scale foundation model training. So there have been many work and study tackling this problem with less data or smaller models in various different ways. But the main challenge here is we need to trade accuracy for efficiency, as we illustrated in the symbolic chart. So the key question here is this trade-off necessary? Or can we actually get both efficiency and accuracy during the training? Well, the answer is yes. Sometimes we can get this best of both worlds with hardware-aware sparsity. So I will show you in a minute how, when, and why we can get there. So first, I will present a line of work designing GPU-friendly sparsity from scatterbrain to pixelated butterfly, finally to Monarch. And at the end, you're gonna see a simple and accurate sparsity, which can train a GPT-BERT vision transformer model 2.5 times walk-along time faster on V100 and 25% faster than the most optimized NVIDIA MLPerf implementation on A100. Then I will share several future directions and some preliminary work. Specifically, I will talk about 2 preliminary work on system hardware co-design called Decentralized Training and ACSGD, where you will see a simple activation compression method and scheduling method will allow you to train GPT-3 XL on a 100 times slower network, the same speed as NVIDIA Megatron inside a data center. Great. Let's start with today's sparsity deep dive. So the idea of sparsity, of course, is not new. It has long history in machine learning and also driven fundamental progress in statistics, neuroscience, and signal processing. But the sparsity in today's context in this talk refers to the sparse model training. For example, some variants of pruning, lottery tickets, or other recent sparse transformer method. Here we can precisely define the efficiency to be the walk-along time speed up. So to be more clear here, theoretical speed up measured in flops sometimes is possible, but in walk-along time is very challenging. So it turns out that a whole line of work in sparse training have been struggling to actually have speed up in walk-along time without the accuracy drop. So why is it so hard, and what other challenges they all share? First, it's very difficult and expensive to search and find a sparsity pattern that could maintain the same level of accuracy of the dense models, especially when you're training it. So it's a combinatorial problem. So many methods like pruning or lottery ticket actually needs to maintain the dynamic sparsity mask, but this large overhead of evolving the sparsity mask can significantly slow down the training and complicate the implementation at the same time. The second is most existing method there's some famous trade-off between the structure unstructured sparsity and accuracy. So unstructured sparsity, which can be efficient in theory, but if not taking into account the efficiency of the training hardware like GPU or TPU, which is especially optimized for dense computations, then there's a problem. Here's an example of the memory access. Compute is very similar. That the point is, for GPU or TPU, this block device, the access of this red spot is the same as this blue 4x4 locations. So even with the 99% of the random sparsity, we'll like to access the full matrix because of this. And finally, most of the method will target a single type of operation, such as tension or maybe large output space, but different model architectures often compose different modules. And in many applications, MLP layers are the main training bottleneck. And in addition, not only focusing on training, but there are many other phases that face different challenges in efficiency. So what would be an ideal sparsity? So the ideal sparsity should be accurate, which can mimic the dense operations, like the dense model accuracy. We don't want any accuracy drop. And it should be hardware efficient. So not only the accuracy should mimic the dense, but the sparse operations should mimic the dense ones, like static and structured sparsity pattern. Well, you also have to have a wide coverage of operators that apply to the most neural network layers, like tension, linear, and in different settings like pre-training, fine-tuning, and inference. So let's go through each of them, each of these challenges and each of this ideal paradigm to see how we can realize the final ideal sparsity. First, what is an accurate or expressive approximation to dense matrices? Well, it's related to the structure sparse plus low rank. So this is the intuition, what I mean by sparse and low rank, and why is it a more accurate and efficient approximation to dense on this simple 4x4 matrix. So say if you want to do a sparse approximation, best we can do is start figuring out with the high magnitude entries. And obviously, we can do a good approximation. And similarly, look at these high values. In the diagonal, we can approximate it well with the low rank matrix, since this is basically full rank. But if we combine these two in an exact way, or the right way, we can see we can exactly represent this dense matrix with a rank 1 matrix and 1 row and 1 column sparse. So we can simply use this intuition on better approximating the attention matrix in, for example, transformer models. And of course, this matrix usually models the pairwise interaction of different tokens. In this case, I love randomized algorithms. And the darker color will represent the score and the interaction. Higher score represents higher interaction. And this is the bottleneck to the model with long range sequences. So if we have a paragraph or a code, or instead of a short phrase, it will be a big matrix scaling quadratic with respect to the input sequence length. So again, if we don't want to compute and materialize this full matrix, we can do some approximation. And we can characterize the existing ones, or the major ones, into two groups. First one is exploiting the sparsity, like sparse transformer, reformer, and the low rank properties of the attention, like linear transformer, performer, and so on. They usually work well in different cases. For the tasks like language modeling, or these ones that really rely on this sparse interaction between a few tokens, so usually sparse approximation will do better. And for the tasks like summarization, classification, and so on, which you need some global information, where the low rank approximation will do the job. So in the scatter brain, how we show that is like you can simply combine this sparse and low rank component in this simple and exact way, and you will get probably better approximation. Analysis dig into when this will have more advantage. So the result is that this kind of generation process arises a lot in attention matrix. And it turns out this structure, sparse or slow rank, has been very well studied in statistics and signal processing since the late 2000s. Naturally generalized low rank and sparse matrices just has been rediscovered in this transformer setting. Of course, robust PCA. So seems like this sparse and low rank structure is pretty expressive and accurate. And the low rank part is too small dense matrix multiplication and also efficient. Then what is the problem? So the problem is the sparse part is dynamic and unstructured. So it is not hardware efficient. So recall we wanted to be static and block aligned, which can mimic the dense operation, but still have the power to represent all this dynamic sparsity. Again, it's a combinatorial search, but show you in a minute that such sparsity pattern do exist. So it's related to a class of structure matrices called butterfly matrices. And I will walk through some simple examples to understand why this can represent any sparsity. So representing any sparse seems to be a very hard problem. We can first take a look at a special case of this sparse matrix called permutation matrix. And we can understand different ways we can represent them. So here's a small exercise. This is the bitwise representation from 0 to 3. And if we look at a permutation that has allowed them to swap the last bit. So 0, 0 and 0, 1 can swap or not. 1, 0 and 1, 1 can swap but not. They decide to maintain. So in this case, how can we represent this permutation matrix? Well, the permutation matrix will look like this. So if you multiply this matrix to from our x0, which represents 0, 0 to 1, 1, we indeed perform this permutation. And what can we observe here? So we can observe that this corner matrix controls the position of x0 and x1. And this right bottom block controls the position of x2 and x3. So this location of 1 or 0 decides if we're going to swap them or maintained. So we can conclude that this sparse matrix can represent any permutation that's swapping indices differing only in the last bit. So those blue locations here are the non-zero entries. And we can remember this sparsity pattern. And jump over the details. If we allow them to swap their second to the last bit. So these 4 positions will control the swap of x0 and x2. And these 4 positions will control the swap of x1 and x3. So now this sparse matrix can represent any permutation that swapping indices differing second to the last bit. So it might not be that obvious, but if we can put these 2 matrices together, we can represent any 2-bit permutation matrix. And similarly, if we combine all these 4 matrices, we can represent any 4-bit permutation matrix. So recently, our lab proved that for these matrices called butterfly matrices, the product can represent any sparse matrix with the near optimal time and space complexity, even with this fixed sparsity pattern. So this generalization from permutation to any sparse is also surprising to us. And recall, let's zoom out. So our goal was to find the ideal sparsity to start with and the fixed one. So this one gives us an opportunity to sidestep from the combinatorial problem of searching over all the possible sparsity pattern at a minor cost of an extra log factor in a number of parameters. And because of the sparsity pattern is fixed, this is also trainable with, for example, just gradient descent or on just the non-zero entries of those matrices, which is a nice smooth optimization problem. So just a side note that is what is even better is usually those matrices, which is a class of fast linear maps that encodes the schema, can represent any structure matrices like the ones that you heard of, like DFT, sparse, low rank, convolution, Hedmond, and so on, and is closely related to the pattern in the vast transform method like FFT because of the divide and conquer structure. And for the audience who is familiar with the network switching, this is the same pattern in the butterfly networks from the 1965. So butterfly matrices are so powerful. Why can't we just directly use them? So here are the challenges to directly adapt them in the modern hardware like GPUs on the left. And there are some simple fixed, we can make it more efficient while still retaining their favorable property. And I can go through them one by one. First, if you take a look at the sparsity pattern, they're not structured. They're fixed, static, but they're not structured. And recall that what we showed earlier about the memory access. So we want this block size to be 32 for at least 32 for GPU or 128 for TPU. So this sparsity pattern currently is not efficient. A simple fix is we can directly reparameterize them with this constant, like the 32 or 128, depends on what the block size you want. We can still tightly represent any sparse matrix with this extra log factor. It's a constant, it doesn't change anything. So even we have this block butterfly, it is still not efficient because they have many products. So we know that if we have a series of operations, we need to do a lot of read and write. And also in the training, if there are more matrices, it's not that stable. So a simple fix is one of the first try was we proposed this flat block butterfly, which we can take the first order approximation to the butterfly matrix, turning this product into the sum. So in this way, is going back to a single sparse matrix. But what is the problem? So the problem is, of course, turning this first order approximation breaks nice properties of the original butterfly matrices. And it can no longer represent a lot of other matrices that originally it can represent. So luckily, to compensate this reduce of expressiveness, we already had this low rank term in the proposal. So you can fix this a little bit. But we want to understand that is there an alternative or a better way that we can still maintain the expressiveness of butterfly matrices, but being efficient? Well, of course, the answer is yes. So more recently, we have an extension on the pixelated butterfly called Monarch. Recall this divide and conquer structure for butterfly matrices. The matrix view is on the right. So the leaf layer will indeed have the optimal big O n log and non-zeros with the log and butterfly matrices. For example, to represent any big O n sparse, butterfly needs to have big O n log and non-zeros. This is optimal. But if we take a look at the second layer, the total number of non-zeros in the second layer becomes n squared of n. So obviously, theoretically, there's a big gap between this square root of n and log n, and so it's not optimal. But the good thing about this two matrices is there are only two of them. And if you look closer, they're super structured. So one of them is naturally block diagonal matrix. So basically, if you combine the first half of the log n factors of butterfly is naturally block diagonal. And the other matrix is kind of structured, but needs some work. For example, the permutation is up to a very simple permutation, also block diagonal. So in this way, Monarch matrices is a simple product of two block diagonal and two fixed permutation matrix. Can be very efficient on GPUs or TPUs. So Monarch is a very interesting result of interplay between theory and hardware. So they're not optimal in theory. Is n squared of n instead of n log n, but also not the most hardware efficient one because it's not a single matrix and it's not dense, but it's the best design if you consider both. So since this is a superclass of original butterfly matrices, can also represent any structure matrices. So it's a kind of a superclass of butterfly matrices based on the parameter counting. Well, so we're almost there for this ideal sparsity. Need one last piece on the different settings. So both pixelated butterfly and Monarch can obviously perform sparse pre-training, but what about the other settings? So it turns out that Monarch can unlock 3 different ways of using the sparse models, including training large-scale models from scratch, like what we just described, and dense to sparse fine-tuning or inference. So say if we have a pre-trained GPT, pre-trained BERT, if we want to have a faster fine-tuning or efficient model serving, this is also doable. And also inverse sparsification, which can transform a sparse model to dense. So how can we utilize this available large dense model to perform this sparse fine-tuning or inference? So this problem reduced to, can we derive a projection algorithm or decomposition algorithm to find the closest ones belongs to that class of matrices? So this is actually a very hard problem for most class of matrices. The only known solutions or popular solutions, algorithms, are for element-wise sparse, which you just pick the large magnitude, and low-rank decomposition. For example, our lab spent years working on this interesting theory problem on what's the projection algorithm for butterfly matrices, for these log n matrices. But fortunately, this is probably as hard as the tensor decomposition, and we haven't solved it. But surprisingly, we found there exists such algorithm for Monarch matrix because there are only 2. So again, this hardware efficient design coincidentally help us make some progress or understanding on the theory side. So I will jump over the details for what exactly this algorithm looks like. That's very interesting. It's based on a recursively call for the rank 1 decomposition. But the key message here is after decomposing this dense matrix to the closest 2 block diagonal matrices up to permutation, you can utilize the pre-trained dense models and enable fast fine-tuning or inference with those Monarch matrices. And the last way is sparse to dense through the reverse sparsification. So in this process, we can start with a sparse model, say train 80% of the time, and then transition them to the dense model to finish. So the training in the remaining 20%, of course, is still dense, but it's important for some applications, for example, the large language modeling, when certain amount of parameters seems to be helping with the performance. So if we still want to maintain the certain perplexity or certain performance, but still save some time for your training, this is the way to go. So next, I will show a subset of the evaluation results. We evaluate on the all settings and, of course, on the wide range of the task. And besides on the standard computer vision and NLP benchmarks, we'll also evaluate on the MLI reconstruction and PDE solving, since Monarch matrices or butterfly matrices can represent any structured matrices. So it's highly related to the FFT. So here are some numbers. First evaluation was on standard image classification on ImageNet. The experiment was on the MLP mixture, emerging architectures and vision transformers. We showed that even with this very simple fixed sparsity, we managed to train model up to 2.3 times faster than the next model without lowering or hurting the model accuracy. The second one was on the large language modeling. The table on the top right shows the result compared to GPT-2 on open web text. We show that we can train the model up to 2.5 times faster than the next model, also without the perplexity drop. Here we can also say a bit about the scaling law. So there are potentially more savings with larger models when we vary the size to do the sparse modeling. And the third one is fine-tuning BERT. So the table on the bottom shows the Monarch matrices fine-tuned model with very similar quality with the dense BERT model, but 1.5 times faster in speed. And also two tests, which we show Monarch outperforms FFT and CN on MRI reconstruction when there's a need to weight different frequencies for de-aliasing problems on the applications, like partial differential equation solving when there's a non-periodic boundary conditions, because Monarch can generalize Fourier transform. And our implementation is 25% faster than the NVIDIA super optimized implementation on MLPerf. And so now I'll show you how we exploit model sparsity with algorithm design, adapting to the hardware, getting this best of both worlds from scatterbrain to pixelated butterfly and to Monarch. But I will talk about several future directions and ongoing work or preliminary work. So the first one is the algorithm system hardware co-design. So super excited to continue exploring more efficient sparsity and actually co-design with the new accelerators. It's very hopeful that this dynamic sparsity can be lower power, if not faster, on the next generation of ML training hardware. But as we know that the hardware design cycles is much longer. Meanwhile, maybe we can exploit all the current available underutilized ones. So I will show our results on communication efficient decentralized training. So the GPU market shipped almost 100 million units last year, but many of these GPUs are underutilized. So leveraging this fact that the volunteer computing projects like Coding at Home, Learning at Home have sourced a lot of NVIDIA and AMD GPUs continuously. And this kind of incremental electricity cost of running a V100, for example, for a volunteer are 100 times slower than on AWS. So if we could make use of all this device in the decentralized and open volunteering paradigm for foundation model training, this would be a revolutionized alternative to expensive solution offered by the data center. So of course, this vision inspired many efforts in decentralized training, but one of the main bottleneck is the communication over this heterogeneous slow network. So first, this foundation model is giant. So we need to go beyond vanilla data parallelism. And second, the network connections between the GPUs are slow and heterogeneous. So we also need to carefully schedule the communication among the GPU device for different parallel training communication paradigm. So formally, we can formalize our problem in the fully decentralized setting, where each pair of device may have different delay and bandwidth. So we can limit our scope on the data parallelism and pipeline parallelism. So in the pipeline parallelism, the model is partitioned into different stages, where in the forward propagation, the activations are sent from stage I to stage I+1. while in the backward, the gradients needs to be synchronized as well. And when combined with the data parallelism, the gradients of the parameters for the same stage needs to be also synchronized. So we can define a tasklet as the forward and backward computation of stage for a micro batch. The goal of our optimization problem is to find an assignment strategy that matches those tasklets to device so that the communication cost is minimized. So this is an example of, this plot is the example of how data and pipeline parallelism work with 4 devices. So how we assign different computational tasklets corresponding to a micro batch and a subset of layers to a collection of geo-distributed devices connected with heterogeneous slow networks. So in this setting, we have to consider potentially exponentially many more distinct allocation strategies because the heterogeneity of the communication matrix. Even this subproblem of finding the best pipeline parallelism strategy is close to our hard open loop traveling salesman problem. So to capture the complex and communication costs for training foundation models, can formulate this problem involving decomposing the cost model into 2 levels. The first level is a balanced graph partition problem showing on this plot, corresponding to the communication cost of data parallelism. Whereas the second level is a joint graph matching and traveling salesman problem corresponds to the communication cost of the pipeline parallelism. And I will jump over the details of how exactly this bi-level scheduling works. So let's say we have a perfect scheduling, which we minimize the communication cost, but it doesn't mean that we don't have to communicate. So there's still an overhead. So how can we be smart about the communication that is done during the forward and gradient passing? Well, gradient compression has been widely studied for data parallelism. Previously, people have noticed that neural network can tolerate some compression for activations. However, to directly compress the activations the same way as how we quantize the gradients have some fundamental drawbacks. So theoretically, simple compressing this activations in a stochastically unbiased way will lead to biases in the gradients that cannot be measured easily or expressed in the closed form. So in another word, it's going to affect the training accuracy a lot. And empirically, this approach leads to this suboptimal quality under the relatively aggressive compression on many models, like we illustrated in this plot. So if we do that in the fine tuning, sometimes it's worse than the zero-shot results. So here's an example of fine-tuning GPT-2 with different activation precisions in the communication. So fortunately, we made an observation that the activation changes of same training examples, we can call it delta, are easier to quantize than the activation themselves. So this gives us an opportunity to redesign what to send in the activation communication. So the intuition here is we can compress the change of activation for the same data samples across epochs to enable an interesting self-enforcing dynamics. So the more training stabilized, the smaller the change of the model across epochs. And then the smaller the changes of activations for the same training examples across epochs will be, which will lead to smaller compression error using the same number of bits. So the training is stabilized more. So here's an overview of how exactly it works in the forward propagation, given a random sample data point. If it has not been seen before, will compute its activation, cache it in the stage 1, and then send it over to stage I+1. Otherwise, we'll quantize the difference between the current activation and its memory from the last update, and then this quantized difference to stage I+1, and update the memory by this quantized difference. And in the back propagation, we directly quantize the gradient, similar to any other existing approaches. So here are some interesting results. So ACSGD is activation compression algorithm with rigorous theoretical analysis that allows the convergence rate of 1/√T without relying on assumption of unbiased gradients. And empirically also achieves the 2x end-to-end speed up compared to that of, let's say, P32, and successfully illustrating this importance of communication compression in the slower networks. And more notably, as we mentioned in the beginning, if we combine everything together, all this scheduling, system optimization, communication compression, when the network is 100 times slower, from let's say 10 gigabits per second to 100 megabits per second, the training is only about 1.1 times slower than the NVIDIA Megatron in a data center. So if this system were to be deployed in a real-world geo-distributed decentralized network, the training throughput of this fine-tuning task will be almost as fast as the performance inside a data center. So of course, there are many more challenges and questions that are answered, like fault tolerance, or what about inference, which has totally different computation and communication challenges, but it is mostly important if we're able to, is deciding like we're actually gonna make it a product, right? Which is coming soon, but at a high level, besides the weight quantization, like the recent work like integer 8, smooth quant, GPTQ, we can exploit the activation function as well. And also the residual connection. And also, another very exciting thing is the data and sample efficiency. You probably heard this swing from model-centric to data-centric AI. And it's possible we can find structures in data and speed up training from a different angle. And the center question is, what is the scaling of training data for a model to reach certain quality? And there have been many great work recently about data distillation, data diet, data pruning from the FAIR group, and very excited to pursue this direction. And because under some computational constraints, the key is to find more efficient ways to learn from the data. So one possible direction, it may be to incorporate the non-parametric algorithms like retrieval or near-neighbor search during the learning process. The intuition is like from the Sparse model training, which has used those algorithms to implicitly increase the model capacity without more compute, and as well as a line of work in the retrieval models like retro from DeepMind. And hopefully we can answer this under the weekly or unsupervised setting where we have a lot of data. So, and also there are several applications going beyond the traditional ones where the researchers have been looking into. For example, the computationally fluid dynamics, medical imaging, DNA sequencing. Actually, many algorithms that we've been using for exploiting model or data sparsity might not only be able to speed up the training, but also unlock the big performance improvement in those applications. For example, near-neighbor search algorithm like hashing, or those structure matrices which can generalize Fourier transform, right? So the sparsity as the inductive bias equipped with this learning capability can only be more powerful. For example, we've been recently working on applications like new material discovery by ML models for approximating the density functional theory, and also for antenna design through ML models for solving those Maxwell equations. Oh, I guess this is the end of the talk. Thanks so much for listening and joining me today. Hope you enjoy it, and happy to take questions.
All right, thank you. Thank you, Beidi. We have time for questions, please.
Hi, thank you for your great talk. I have two questions regarding your first part and also the second part. For the first part, you mentioned something that the block diagonal matrix is not optimal to approximate the dense matrix, but it's good enough in performance. Is it because the model you try to train is too over-parameterized, so we don't need to be precise? We just need to some good enough metrics to do the training. Then it can give us the good enough accuracy. And the second question is regarding the second part. You mentioned something when you do decentralized training, you first need to do some data partition. So what kind of data partition you are doing? Does that affect your performance? Yeah, thank you.
Yeah, thanks for the question. So let me try to iterate on if I understand the question correctly. So the first question is to ask why we can actually use a sparse matrix to actually mimic the dense operations or the dense performance. Is it because the models are too over-parameterized so that even any kind of sparse one could work? In short answer, I think that's a yes. So the larger the model is, the more over-parameterized it is, the more headroom we can enforce the sparsity there. But a more detailed answer would be not exactly any kind of sparsity would work. So those kind of sparsity can maintain, for example, the Monarch matrices can maintain the accuracy not only because is block diagonal and efficient, but also all this permutation. So this two block diagonal with the permutation can exactly represent the original butterfly matrices. And butterfly matrix is very expressive. It will be kind of a more general matrix than any other like sparse matrix. So that is the reason why it's a combination of the model is indeed very large. And also the algorithm is kind of smart. And for the second question, it's about the decentralized training. The question was, do we need to partition the data in a certain way so that we can maintain certain accuracy, and how we partition that? If I understand that correctly, are you talking about this part where about the data parallelism? That's just kind of random data partition for micro batches. So if you're talking about this part, about the communication compression, I was talking about for the same sample, if you see that on the same device, if you see that from epoch 1 and epoch 2, the difference of this activation can be quantized more. So there's no data partition involved in this part as well. So maybe I misunderstand something.
Yeah, you're correct. You understand it correctly. Yeah, thank you.
Okay, thank you.
All right, thank you. Next question, please.
Hi, Beidi. Thanks for the interesting talk. I know you've always been a strong advocate for smart algorithm design over hardware acceleration. Some of your earlier work on dynamic sparsity was used to train large DNNs on devices using nothing but CPUs. With the advent of foundation models, and as models continue to grow larger and larger, have we, even with structured matrices, dynamic sparsity, et cetera, have we crossed that point of no return where we could train models, such as foundation models on low fidelity devices using nothing but CPUs? Or is there still hope to train such large models using intelligently designed algorithms?
Yeah, thanks for thanks for the question. So it seems like you know my earlier work called Slide, which I code up the whole MLP training from scratch on C++ on CPU just to demonstrate that hashing can make the prediction for the computation that actually needs to perform and make CPU faster than at that point, the GPU. Yeah, thanks. I'm very happy to hear about that you're a big fan of that work. And the reason why I kind of moved to different kind of hardware devices, for example, on GPU, and now on like more decentralized devices, is I figure out that when the model becomes like larger and larger, is great to have algorithms to adapt to different kind of hardware. And with a combination on the C++ work or the CPU work was now a startup. So it's more like into the production and trying to help people who have all these CPU clusters to train recommendation models faster. I think it might be coming back. Because for a long time, I can't find such a large matrix that I can actually make CPU faster than, there's such matrix that there's more headroom for CPU to catch what GPU can be doing. Because for the transformer, which is kind of the major model architecture, the largest used to be like, for example, several K by several K. This is a very relatively small matrix if you want to do any matrix level optimization on it. The speed up we can get on Slide and the C++ work relying on you need a really large matrix, for example, in the recommendation models. So it's a little bit more constrained, but luckily or unfortunately, now the model on the 175 billion parameters have the matrix, which is 10K by almost 50K. And it also demonstrates this extreme sparsity. So stay tuned, Slide is coming back.
Thank you.
Thank you.